Like you already said, Nestor, my name is Manuel Perger. So thank you very much for this opportunity to talk, to give a talk on my latest research, which tries to connect the Gaussian process kernels with actual stellar spot distribution models. So normally we use the Gaussian process regression to mitigate the effects of stellar dark spots on a rotating stellar surface. And we have quite a nice tool with StarSim at hand to model such data. And so what we wanted to know is how is such a radial velocity data actually characterized by different stellar spot distribution models? How do commonly used Gaussian process kernels actually adjust on those data? And if there is any possibility to improve on that process. So we already know, of course, that every signal produces covariances in radial velocity data, and we can illustrate those with the autocorrelation function. So what we have done is we have put one single central dark spot on the stellar surface, and with StarSim we have created radial velocity data.
Manuel?
And here on the side we see the autocorrelation.
For some reason, the slides are not advancing.
Oh, that's a bad thing. For some reason, okay.
Yeah, we're seeing.
Maybe try.
We're seeing the PDF
screen and then sharing again.
Right.
Yes, something is wrong. You're right. Sorry.
Go ahead. No worries. There you go. Well, now we can see your slides. Go ahead.
So you saw that one? Sorry. Well, whatever.
So go ahead.
Yes, I got it. So here on the left side, you see the autocorrelation function of radial velocity data made with one single central dark spot. So this is quite characteristic. We see a periodicity, which we chose here to be 25 days. We see zero correlation, of course, at half the rotation period, and we see those characteristic negative lobes on both sides. Here on the right side, I also show the relation the correlation function has with filling factors on top and at the bottom with the sinus of the inclination. Nevertheless, this is not a very realistic model. So we searched the literature and we find actually 4 stellar distribution models which can be found. So the spots are, of course, those characteristics are numbers, appearance date, location, size, and also their lifetime, which we chose to be a constant 100 days in our case, since this is a very important parameter in the Gaussian process regression. So we have this spot distribution around 1 active longitude at the top and around 2 active longitudes at the bottom. On the right side, we see the radial velocity data we have made with those spot maps, and we can see if the longitudes are always the same. We don't have a change in phase, and we see the periodicity of 25 days is quite constant over time. And this is different for the stellar spot distribution of a few large polar spots, and also for the random distribution, which diminishes with the lifetime of 100 days. No? We see that on the right side. So what is quite characteristic here is that the contribution at half the rotation period is changing with the stellar spot distribution model. So what we're actually seeing is the relation between the side where we have the most prominent spots and its opposite side. So for the 2 active longitude model, the correlation is quite large. And for the 1 active longitude model, this correlation is close to 0. So now, how do the Gaussian process kernel actually compare to those? On the left side, we see at the top the quasi-periodic kernel, which is quite commonly used. We see the periodicity every 25 days. We see also this exponential decay. And in the middle, we see the simple harmonic oscillator showing both of those effects also. And on the bottom, we see actually a result of our work where we connect the best features of the quasi-periodic kernel and the contribution at half the rotational period. We call this the quasi-periodic and cosine kernel. A quick look at the formulation. You can always see it is constructed of two components. One is an exponential decay. In the case of the quasi-periodic kernel, this is always in a quadratic form. In the case of the simple harmonic oscillator, in a linear form. And we have this periodic component. In the QPC case, you can see we have with H1 and H2, we have two amplitudes. One is connected to the quasi-periodic component, the other just to this cosine function. No? So, and those are now the results of our work. So for every spot distribution model, which we again see from top to bottom, we have calculated 5 iterations, which we see here in black. And we see the best fits on those radial velocity data for the different kernels. In blue, the quasi-periodic one, in green, the harmonic oscillator, and in red, the quasi-periodic and cosine kernel. So if we now take a look at how those Gaussian process kernels really extract the rotational period, we can see that the quasi-periodic kernel for every spot distribution model is able to extract the rotational period, whereas for the harmonic oscillator, it gets distracted by the contribution at half the rotational period. And it goes so far for the 2 active longitude model that instead of the rotational period, it always catches half the rotational period. Similar things are true for the lifetime. So for the quasi-periodic kernel, it always catches the 100 days lifetime of the spots introduced into the data. The harmonic oscillator is rather catching on if the periodicity is stable. So if we have a phase shift in the active longitudes or not. And yes. So what I just said is here the table, the same results, more or less. I highlighted here some numbers in red. Those are the differences in log likelihood. We can see that in all cases, the QPC kernel gives the best fits, accounting for this contribution at half the rotational period. And I also highlight in here the filling factor of the prominent side, so the side where the most prominent spot is visible, and its opposite side, and we can see that it increases from the stellar spot distribution model as shown on the right side again. No? So this contribution is the connection between amplitude H1 and H2. So to sum up, single produced covariances, and we can see those then in the autocorrelation function. If we look at the autocorrelation function of just one spot model, so we can see the periodicity at the rotational period. We can see that it is 0 at half the rotational period, and we can see those characteristic negative lobes. If we take a look at the autocorrelation function of those multi-spot models, we can see that the time decay is correlated with the lifetime of the spots, that the signal persistence is rather connected to the phase stability. And then we have a characteristic contribution of the correlation factor at half the rotational period, depending on the stellar spot distribution model. And that is why we constructed this quasi-periodic and cosine kernel, which connects the best features of the quasi-periodic kernel and adds a cosine term at half the rotational period, resulting in the best log likelihoods, the best additional jitter, and actually bases these kernels only on physically relevant parameters. Yes, and this is my work I wanted to present. Thank you very much.
Thank you very much, Manuel. So we're opening up now for questions. I don't see any in the Slido right now. I do have one question regarding the quasi-periodic and cosine, this new kernel that you have. Is this easy to map with George, for instance, like from a computational perspective? Is this fast? How what's the speed increase or decrease with regards to the simple harmonic oscillator? Is this a George kernel? Is this accelerated kernel?
Yes, in the paper I give the code to implement into the George code. This is of course not a good solution. The Celery code is much faster, much better. but it's quite important that my work doesn't really comment on the code itself. It's just an analysis on what kernel to use and what that I think it's quite important to base the parameters of the kernel on really intrinsic characteristics of the star, and this was the work.
Right.
So unfortunately it's not implemented in the Celerite code, but there won't be any problem to code it. I think actually they have a similar approach, adding some simple harmonic oscillator, but it's always the problem that it doesn't really catch the lifetime because of this linear exponential decay they have.
Right.
And there might be some place for improvement.
Okay, that's great. Thank you, Manuel.